Welcome to this explainer. Today, we're stepping straight into the lab to tackle one of the most critical, yet honestly frequently overlooked security flaws in network infrastructure. We're talking about the default switch configuration. We're going to take a single Cisco switch and transform it from a completely open, vulnerable landscape into a fortress of logically isolated networks using VLANs. If you're an IT student, a network professional, or a CCNA learner, mastering this layer 2 segmentation is absolutely essential. So let's get right to it and build some invisible walls. Okay, let's dive into this. I want you to imagine a busy hospital. You've got nurses updating patient charts, radiology transferring massive X-ray files, and the billing department processing credit cards. Now, what happens if the billing department's computers can just freely communicate directly with the radiology servers? Well, that's a compliance nightmare. It's a massive security risk. We simply cannot allow a completely open network where highly sensitive departments are just exposed to one another. When you have zero network segmentation, it is just chaos. Out of the box, a Cisco switch places every single port into the exact same default state, which is VLAN 1. That means every single device plugged into that switch shares the exact same broadcast domain. Billing can reach nursing. Radiology can reach admin. If just one machine in the billing department gets compromised by malware, that infection has a direct, unobstructed path to the entire hospital network. That, right there, is the vulnerability of a flat network. To really prove the severity of this, let's run a quick baseline diagnostic. We have nurse 1 sitting at IP address 192.168.50.20, and we send a ping request over to X-ray 1 at .60. We get 4 replies, 0% packet loss. It's a complete success. But hear me clearly on this. In the context of network security, this baseline success is actually a massive failure. Before VLANs are configured, everything can reach everything. And we urgently need to fix that. Now, what's really fascinating here is the central paradox we're about to solve. We've got 9 active devices spread across nursing, radiology, and admin. And if you look closely at their IP addresses, every single device exists on the exact same 192.168.50.0/24 subnet. They all share the exact same gateway. So the trick here, and really the magic of VLANs, is that we are going to logically isolate these 3 departments without touching or changing a single IP address, not one. To pull this off, we're going to follow a really strict configuration path. First, we assess the flat network problem. Second, we construct our logical VLAN domains. Third, we assign the physical switch ports. And finally, step 4, we achieve absolute layer 2 isolation. All right, step 1 is constructing our logical boundaries. We'll drop right into the switch's command line interface, hop into global configuration mode, and start creating our VLANs. We type VLAN 50 and name it nursing. Then VLAN 60, name it radiology, and VLAN 70, name it admin. Simple enough, right? But here's an absolutely crucial concept to grasp. Creating a VLAN only builds the isolated domain. Right now, VLANs 50, 60, and 70 are basically just empty rooms waiting for occupants. They literally don't do anything at all until we actually assign ports to them. To assign those occupants efficiently, we need to understand a super powerful CLI tool, the interface range command. Take a look at the syntax. We type interface range FastEthernet 0/2 through 4, FastEthernet 0/20. Notice how we use the hyphen to grab a consecutive block of ports, so ports 2, 3, and 4, and then we use a comma to grab a completely non-consecutive scattered port, which is port 20. This is great because it lets us grab all the specific physical ports belonging to the nursing department in just one single line of code. Now we get to execute the magic. For each department, we select their specific ports using that interface range command. Then we type switch port mode access. This just tells the switch that these ports are for end devices, like PCs, and not for trunking over to other switches. Finally, the defining command, switch port access VLAN 50. This right here is what physically moves those nursing ports off the flat network and drops them into our secure, invisible wall. We just repeat that exact same process to move the radiology ports into VLAN 60 and the admin ports into VLAN 70. So how does this actually reshape our overall switch architecture? Well, a fundamental rule of networking is that a switch port can only belong to one data VLAN at a time. Remember, we started with all 24 ports sitting out there in the default VLAN 1, but as we configured our secure domains, we pulled 4 ports for nursing, 3 for radiology, and 2 for admin. Because of that, our default VLAN safely and automatically shrinks down to just the 15 unassigned ports. The flat network is officially dismantled. Okay, the configuration is done. Now we move to the proof phase. First things first, we need to validate that our departments can actually still work internally. So we have Nurse 1 at IP.20 pinging Nurse 2 at IP.21. Both of these devices reside perfectly within VLAN 50. And sure enough, the traffic flows uninterrupted within that secure domain with 0% packet loss. So the internal network is perfectly healthy. But honestly, internal communication was never the problem in the first place, right? The true measure of our success comes down to what happens when we try to cross these newly established boundaries. We're about to recreate the exact same ping that succeeded back in our baseline diagnostic. But this time, our invisible walls are firmly in place. All right, here is the payoff moment. We're back on Nurse 1 in VLAN 50, and we try to ping X-Ray 1 over in VLAN 60. Request timed out, 4 packets sent, 0 received, 100% packet loss. Let that sink in for a second. Our expected failure is actually a complete success. The invisible walls are holding. Communication from nursing to radiology is completely blocked. But as networked professionals, you know it's never enough to just know that something works. We have to understand why it works. So think about this crucial point. If Nurse 1 and X-Ray 1 share the exact same 192.168.50.0/24 subnet and their IPs are perfectly valid, why exactly did that ping just fail? And this brilliantly illustrates the hidden mechanism of network communication. Before an IP packet can even be sent, the computer needs a MAC address. So Nurse 1 sends out an ARP broadcast, basically yelling out to the network, hey, who has 192.168.50.60? Now, the rule of a switch is that broadcasts flood to all ports in the same VLAN. So the ARP request floods perfectly everywhere within the nursing VLAN 50. But broadcasts are absolutely blocked at VLAN boundaries. They hit that invisible wall. X-Ray 1 never even hears the question, which means it can never reply. This right here is a massive aha moment in networking. Layer 3, the IP level, identifies logical networks. But Layer 3 relies entirely on Layer 2, the broadcast level, to map those IPs to actual physical MAC addresses using ARP. And VLANs, they'd operate exclusively at Layer 2. They physically trap that broadcast traffic. So even if your Layer 3 IP subnet is completely identical, if the Layer 2 ARP broadcast cannot cross the VLAN boundary, your IP addressing is rendered totally powerless. The isolation is absolute. To ensure our environment stays completely secure, we always need to verify our configuration. Dropping back to the CLI, we can run the command show VLAN brief. This is an incredible command that gives us a clear summary showing our active, nursing, radiology, and admin VLANs, alongside all their properly assigned ports. We can also run show interfaces switchport on a specific port just to confirm it's in static access mode for the correct VLAN. Oh, and never forget the golden rule here. Once everything is verified, type write memory so your configuration survives a power loss and writes to the startup config. Let's quickly recap the core teaching moments from this lab. Number 1. Before VLANs, complete reachability across a flat network is a major security failure. Everything reaching everything is bad. Number 2, sharing the exact same IP subnet does not guarantee connectivity if VLANs are in play. And number 3, VLANs are strictly Layer 2 broadcast blockers. They isolate traffic by preventing the ARP requests that IP communication relies on from ever crossing that boundary in the first place. We've just taken a chaotic, flat switch and transformed it into a segmented, highly secure environment in just a matter of minutes. By manipulating broadcast domains at Layer 2, you seriously have the power to protect sensitive data across any organization. So I'll leave you with this final thought to consider as you head back to your own setups. Are your flat networks currently exposing your critical infrastructure? It might just be time to build some invisible walls of your own. Thanks for joining me on this explainer, and keep building secure networks.